Okay, so now we know phi equals 0, so therefore we know, so I've just rewritten our equation for angular velocity, rewritten that second equation of motion. Again, just be, let's not get too lost in the details here. We have our equation of motion, and we have the first derivative, which gives us velocity, and the second derivative, which gives us acceleration. And we're just plugging in what we know to find out what we don't know. We first plugged in the initial conditions to find out phi, and now we're plugging in into the first equation, and we're plugging in the other initial condition that we know into the second equation in order to find theta max. And that's what we have here. And so therefore, we can solve, this is equal to 4 meters per second divided by 0.7 meters. And so therefore, let me just say that's V0 over L. V0 over L. I'll plug in numbers when we're ready for it. And so therefore, the cosine of 0 is 1. Theta max square root G over L is equal to V0 over L. That's the square root of G over L. G over L. Okay, so we can square both sides. Oh no, we don't have to square both sides. Therefore, theta max, the amplitude, is equal to V0 over L, square root of L over G. I guess we can simplify that. I don't know. We can just leave it like that, or we can say it is V0 over the square root of GL. And I get 1.53 radians. Now that is funny, should be funny, because 1.53 radians, remember, there are 2 pi radians in 360 degrees. So that means there's 6-ish radians in 360 degrees. That means a radian is about 60 degrees. It's 57 degrees. So this is about 90 degrees. So basically what I've done is I've taken this pendulum that looks like this, I've given it a shove, given it a V0, so that it goes all the way up to here. That is no longer simple, right? It's not simple harmonic motion. We can approximate it, we can approximate it as simple harmonic motion, but it's definitely not simple harmonic motion because we can't use a small angle approximation. So I should have reduced that initial velocity by about, it should be about 0.4 instead of 4. For this to be simple harmonic motion, therefore, and I should have asked that question really, to be simple harmonic motion, V0 should be about 0.4 meters per second instead of 4 meters per second, because that will then give an initial theta max of 0.15 radians, which is much more reasonable. That's about 10 degrees, 0.15 radians. Therefore, theta max would be about 0.15 radians, which is about 10 degrees, which would be much more reasonable. We used these equations, right? We used this equation, which assumes a small angle, in order to calculate this. So this can't be right. This can only be an approximation. It's not a good approximation. To be simple harmonic motion, it really needs to be an angle 10 degrees or less. So let's go ahead and just say, we left off the decimal point and call V0 0.4 meters per second. And so therefore, theta max is, instead of 1.53, we'll just say theta max is, change the color, 0.4 meters per second, and we can put the decimal point over here, 0.153. 0.153. Try that again. To go back and look at this problem, we just have to remember that we changed the initial speed to 0.4 meters per second instead of 4 meters per second. Okay. 0.4 meters per second is the angular velocity. And this is the only place we've used it so far. Okay, so we've got 0.153 radians. That's very reasonable. So before we go on to part B, again, using the corrected initial velocity, before we go on to part B, let me just show you that we could do part A a lot easier. No, I don't know about a lot easier, but in a way that's a little bit more familiar to you. And we could do it from an energy point of view, right? We could do it from an energy point of view. We can say, the pendulum, we give the pendulum a push from equilibrium. It's got an initial velocity V0. It's all kinetic energy. It's going to swing up until it stops, where it's all potential energy. So we can conserve energy. K plus U initial equals K plus U final, where the initial energy is 1/2 mv squared, and the final energy is mgh, because the initial potential is 0, the final kinetic 0. Solve for h, and we get 1/2 v squared over g, and so we simply get 1/2 times 0.4 meters per second over 9.8 meters per second squared, and we get 0.082 meters, 8.2 centimeters. Goes up 8.2 centimeters. Okay, so, and then that is the amplitude. Now, that's not the amplitude I was really asking for, because I was asking for the amplitude of the motion given by the equation of motion theta equals theta max sine omega t plus phi, right? So if we look at the equation for theta, the amplitude is theta max there. This is, h is just a different kind of amplitude. It's still an amplitude. It's a maximum displacement from equilibrium, but it's a maximum y displacement, a maximum vertical displacement from equilibrium. It's still an amplitude, right? Because the pendulum goes up to a height h, stops, comes back down, h gets smaller, 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 till h goes to 0 again, goes to the other side, h gets to be a maximum again. It goes up to height h. So it's going to go up to height h on both sides. It's going to go up to height h on both sides and oscillate back and forth those two positions, back and forth between those two positions. So it is an amplitude, but what we're really looking for is theta max. So we want theta max, and theta max, now it's pretty straightforward. It's just given by the geometry of this problem, right? Theta max, we can go ahead and draw a horizontal line here, and we've got a triangle. We've got a triangle here, where the angle theta max is there, the length, the hypotenuse is L, and this side that's adjacent to the angle is L minus h. So therefore, we can say cosine of theta max is equal to L minus h over L. So therefore, theta max is equal to the inverse cosine of L minus h over L, which equals... Well, I found an error in my algebra, and that was that I forgot to pull over this squared here, and so this is 0.0082. 0.0082, h is 0.0082 meters, and because what I found was theta max didn't work, but now let's see if it works. And the cosine of the angle, equals 0.153 radians. Whew. Okay, so... it worked. 1.153 radians is what we found by using our equations of motion. 0.153 radians, a little bit easier to get to using energy conservation. By the way, just in case you're struggling with radians versus degrees, my calculator was in degrees, and just don't forget that there are pi radians in 180 degrees, so you can go back and forth between radians and degrees that way, but when you're doing these problems, we really should be using radians. But you can do conversions that way, right? So your angle, theta in degrees, you multiply it by, this should be pretty easy for you, multiply it by pi radians over 180 degrees in order to get the angle in radians. Okay, that I shouldn't be telling you. Okay, so let's do part B. What is the equation of motion theta t? Well, I think we're pretty much done now. Theta of t is theta max sine square root of square root g over L times t plus phi. We've evaluated everything. That's the point, is that we needed to go ahead and evaluate everything. So we get theta as a function of time is equal to 0.15 radians times the sine. That's the maximum displacement from equilibrium times the sine. 9.8 divided by 0.7. 9.8 divided by 0.7 equals 14 square root 3.74. I guess let's just do two significant digits. 3.7 hertz times t plus 0. So that is the equation of motion with units. And really, let's actually be more explicit. Let's go ahead and say that is radians per second. Radians per second. It's omega. Omega is 2 pi f. That is radians per second. Radians per second times t. And there you go. That's my equation of motion. The equation of motion that describes this pendulum. The pendulum is going to be swinging between 0.5 radians on this side and 0.15 radians on that side. That's theta max. And it takes, and the period. Oh, what's the period? Did we write down the period? I don't know if I asked for it. Oh, no, I never asked for it. But we can go ahead and say, oh, and the period is going to be 2 pi square root. Oh, let's just go ahead and we already calculated it. Omega is 3.7, and the period is equal to 2 pi over omega. So I didn't ask for the period, but we have now calculated everything we could about this pendulum, right? We've calculated the position as a function of time, or the angle as a function of time. We've calculated the equation of motion for theta, for omega. We could very easily write it for alpha. We've calculated the omega, we've calculated the period, we've calculated theta max, we've calculated the phase. Done. Happy day.